61A, Lecture 20 Q&A.
All right, let me ask John a question while we're waiting for everybody to chime in. I've been coding for a lot of years, John, and I have to say, except for like commercial things, I don't think I've ever done object-oriented. Like when I just code internally, even when we build big things. Is that 'cause I'm a crappy programmer, or is there some obstacle still? Like I never build a lot of classes and do all the things that I teach. What's wrong?
Well, object-oriented programming shines in this particular scenario when a bunch of stuff is changing.
Yeah.
And a lot of code that gets written these days, especially data processing code, doesn't really have like mutation going on. It doesn't have
Yeah.
changing state over time where you're like tracking a lot of stuff. This happens more often in like software that's got a user interaction cycle or something like that. So yeah, if you're doing a bunch of data processing workflows, then it just doesn't show
Okay.
up as much.
Yeah, that's a good point. That's an interesting way. I hadn't thought about it that way, but I like that.
Oh, in lecture, I said str is
Oh yeah,
not a
sure.
function, but instead is a class. So if we look at what str is, it says it's a class. Classes and functions are extremely similar in the sense that the way you do something with them is you call them. And so when you call some function like abs, it could really do anything. When you call a class, it's always going to create a new instance of that class. So the str, though it looks like a function, it's really a class. And what you're doing here is you're calling the str class's constructor in order to make a new string. And you can call this on pretty much anything, and it will always make you a string. So in that sense, str is a class.
It's probably a distinction that doesn't really matter that much, honestly.
Yeah, it doesn't matter at all,
Yeah.
but it's interesting to see that
Yeah, how it's
functions
implemented.
and classes are so similar. I mean, right? They're just classes are functions that always create a particular instance of this class. The next question was about a mistake in the Polymorphic Functions video from today's lecture, where I redefined str and repr below the places where I was calling them, and so those definitions had no effect. Yeah, good question. If you print first and then you redefine str and repr, then the print won't know about the redefinition, which I think is just a mistake in the video. But I checked it, and if you rearrange the code, it still does the same thing. So the code wasn't doing quite what I said, but it would have done what I said had I written it right. Does that make any sense? Yeah. So anyway, you're right that if you print before you make changes, then those changes obviously won't be reflected. Okay, so this question is about how addition works when there's an instance of a user-defined class involved. And the answer is it's kind of complicated. So when Python sees x plus y, it checks to see if x is a has a user-defined class. And if so, if it has an add method. If that's not true, then it checks y and sees whether y is a user-defined class that has an radd method. What's radd? Well, this is the method that gets called when an instance of this class is on the right of the plus. And if neither of those are true, then it tries to use the built-in addition that it has, which basically only works for the built-in classes like int and float and str. You know, if that doesn't apply, then you'll see an error, which says, I don't know how to add an int and a widget or whatever you have there. So this multi-step process is not terribly important, except for it indicates just how complicated it is to set up a language so that you can arbitrarily extend what plus does. And it's complicated because there's these two different arguments to the addition. And you know, you might want it to be the case that your user-defined thing shows up on either side, but then sometimes the order matters. It's not always the case that every addition operation is commutative. Like for strings, A plus B is different. Oh, come on. A plus B is different than B plus A. And you might want that kind of behavior in your own version, but then you need to know whether the object you created is on the left or the right of plus. The next question was, for the Kangaroo class, is it okay to use in to check the contents of the pouch instead of using a for statement?
No, I think using the in is fine. The reason I use the for loop and the while loop is I like to exercise that for students to make sure that they understand it. But the in operator is a perfectly fine thing. It's essentially, this is one of those cases where Python has given you a construct that does something that you could have done manually, but you could have absolutely used the in and done it in one line instead of 2 or 3 lines.
Yeah, great question. So the question is instance the same as just finding the type of something and figuring out whether that's equal to a class? And they're oh so close, but because of inheritance, they are actually different. So let me show you an example. If you have a class A that is the base, and you have a class B, which inherits from A and is the subclass, if I build a B and ask, is this an instance of the B class? Well, the answer is yes, but it's also an instance of the A class. Whereas the type of B is the B class, but it's not the A class. So what isinstance does is ask, is B an instance of this class or any of its subclasses?
That's a tricky little thing, isn't it?
Yeah, but it can be useful because
Yeah,
basically
sure.
you're future-proofing your code by saying, is it an instance of a kangaroo? If somebody comes up with this special subclass of like a short kangaroo, your code's still going to run correctly. Yeah, good question. So what's the difference between this built-in repr function and this thing? Well, you'll see them in different places. So repr can show up anywhere. It's a built-in function that's in the global frame. You can call it on anything. And what it will do is really, really simple. It will ask its argument, what is your repr method? And it will just call that. So I can get repr of, basically any kind of object I create. But what is happening there is that there isn't a whole bunch of code within repr that says, here's all the different kinds of objects in the world and here's what they do. Instead, all repr does is take its argument and invoke the method that means this can be defined in the class of whatever this thing is. This happens to be a list. And it has a repr method built into it. You can ignore what a slot wrapper is. That's kind of some random detail of Python that we don't care about. But this is just like some function that that knows how to turn lists into strings. And what does it do? It adds square brackets and commas and spaces in the right place and stuff like that. So the difference is that these are built to be related to each other. These appear in class definitions. So you will have often a repr method, which takes in the object that you're trying to make a string of and returns a string, something like that. And this is a function that's built in that always knows when it gets an object and it doesn't know how to print it out, it just invokes this repr method, this underscore repr method in order to do the work. But if you had called this something else, it wouldn't work. So the relationship is between the repr without underscores being a built-in function and the repr, which is a special method name with the underscores that does the work. So if we make an A now, it will look like A instead of some kind of like funky thing with angled brackets. The next question was whether every class defines repr. Yeah, great question. So the underscore repr method is something that the user has to define in each class. If it's not defined, there's some default behavior, and you've seen it many times. It's this thing where it shows you some angled brackets, and it tells you what the class is, and it says the word object. So like this is built in, but it's not very useful. It's just like a placeholder. And so it's almost always the case that when you create a class, you want to add a repr method that shows more interesting information about A? Yeah, good question. So how would you take a tree and print all the paths? So let's say we want to print first we have to decide what a path looks like. So a typical thing would be it's the list of labels along a path. A path is really like a list of nodes. Each one is a tree, but you know, the interesting part of a path is that it's got a bunch of labels in it that are numbers or whatever. Yeah, so if we take in a tree and we want to print all the paths from the root to a leaf.
Yeah.
I'm gonna move some zoom display stuff.
I don't know how to do this yet, but I know it's going to be recursive, Steve.
You know, the most straightforward way to do this is in 2 steps. You get all the paths, and then you print each one out. So let's try it that way. What would this actually look like if you had a tree? What have I done? Made a mess is what I've done.
I hate this notation, John.
Okay.
I just have to get that off my chest, that's all.
Okay, so we get 1, 2, 3, and we get 1, 4, let's say. That seems like a good way to go. Now, what is all paths? A path comes by finding a path from the root of a branch all the way to a leaf, and then putting the current label at the front. That's like a recursive way to think about a path, is that a path has the first thing, and then it's got the rest of the elements in the path. And the rest of the elements in the path are a path in a smaller tree, a tree that starts at a branch. So one way to do this is to say that for every branch, you want to get all the paths in that branch. Like here's a branch, and a path through that branch would be 2, 3, but we want 1, 2, 3. So if we go through all the paths in the branch, then what we want to return here is not just 2, 3, like path might be 2, 3. We want to return 1, 2, 3. But there might be multiple of them. So I'm going to write it as a generator function. We can change it later if you want. But what we yield here is 1, 2, 3, which would have to have the label of t first, and then the rest. So this is yielding 1, 2, 3, which is what we want.
I don't know if you heard that, but John had this beautiful recursive definition in there. He said, what is a path? It's one, if we start at the tree that he's just described up top, with the path of everything below it.
Everything below.
Right. So there it is. I mean, that one statement is what wrote your function for you.
So now we have to think about what happens when you hit a leaf. Here, there are no branches in a leaf, so this would do nothing, but that's not quite right. When you get to a leaf, there is a path, which is just a 1-length path. So if t is a leaf, then I think we want to yield a list of length 1. Okay, and now that some gardeners have showed up, it's going to be very hard for me to talk, but I'll try anyway. Okay, so that seems to have passed the test. I think that's a good way to print all the paths. And actually, this is exactly the same structure that we had in a question that we had to skip at the end of the last time. Why is there sometimes 2 for loops? The reason there's 2 for loops is that in each particular branch, there could be multiple paths. So let's like extend this example just a little bit. Now what should happen is that we should get 1, 2, 3, 1, 2, 5, and 1, 4. When we pass in t is 1, 2, 3, and we go to the first branch. which is this guy. This actually has two paths through it, 2, 3, or 2, 5. For the branch, which looks like this, there isn't just one path through that branch. There's two. And that's why we have a second nested iteration. It's that for each individual branch, there might be two different paths, and for each one of those, we want to yield a new path. So this is a question about fall 2015, midterm 2, question 3A, and just understanding the question, it is a good idea to read what's there, but then take a look at the examples, the doc tests, to make sure that you've really understood what it does. And if, like, it's doing something that you don't expect, well, then you got to address the wording of the question and try to figure out what's going on. And in an exam, if you really can't understand what a question means, then feel free to ask a question, because there's no point in working to solve a problem if you can't figure out what it's asking. Okay, so implement complete, which takes a tree instance T. I'll tell you in advance that on Friday we'll talk about tree with a capital T, which is that we'll build a tree class, which is just like the tree data abstraction, except it's a class. So you might see some notation in here that's a little bit different. I think all that's really different is that you write T dot branches instead of branches of T, and same with the label. So maybe we could just ignore that for a little while. But I just wanted to let people know that this is something we will cover but haven't covered yet. Okay, so which takes a tree instance T and two positive integers D and K, and returns whether T is DK complete, which is some term that's made up for this question. A tree is DK complete if every node at a depth less than D has exactly K branches, and every node at depth D is a leaf. The depth of a node is the number of steps from the root. The root node has depth 0, built in all function blah blah blah. It's not really relevant. The thing to think about with this is like, what the heck does this say? And looking at examples and thinking about examples is really important to figuring out what this means. So let's see what the example says. So a tree that has a node at depth 0, but no other nodes, is apparently DK complete for D equal to 0, because the depth is 0, and K equal to 5, and it seems like this 5 is just kind of irrelevant. What's going on here is that every node at depth less than D has exactly 5 branches, but there are no nodes less than 0 depth. 0 is the smallest depth. So all that matters here is it the case that every node at depth D, which is 0, is a leaf? And that is true. So this has only one node, its depth is 0, and it is a leaf. And therefore, this happens to meet the definition kind of by accident. It doesn't have any nodes at less than 0, so this 5 becomes irrelevant. But that's why this came out as true. Okay. Let's look at a more interesting tree. So here's a tree that's got 3 branches and each one is a leaf. Is it the case that this tree is 1, 3 complete? Yes. Because for all the nodes at depth less than 1, which is just 0, it has 3 branches. And U itself, the root, is the only node that has depth 0. And it does, in fact, have 3 branches. And then all the nodes at depth 1 are leaves, and that is true. Tree. Is it the case that this is depth 1, 2 complete? No, because the root has 3 branches, not 2. Is it depth 2, 3 complete? No, because the nodes at depth 1, which is less than 2, like this one, don't have 3 branches. It's just a leaf. It doesn't have 3 branches. It has 0 branches. So that's why this is false and this is false. And what about this tree? Well, this is a funny tree. This is a tree where 1 is at the root, and then it has 3 branches, which each look like U. So if we were to write this out, it would be pretty long to write out. It would be a tree with 1 at the top, and then 1 in the middle 3 times. And then each one of these middle nodes would have 3 leaves under it that are all 1s. So there would be 9 different leaves. And that is a 2-3 complete tree, which means that all the leaves are at depth 2, and everything in between has 3 branches. How might you approach this kind of problem? The base case here is that you've hit a leaf. Whether a leaf is dk complete really depends on what d is. So leaves are okay if d is 0. We saw that in this first example. But they're not okay otherwise. We saw that in this example. If there's a leaf at depth 1, and this is supposed to be depth 2, has all the leaves, then you've run into a problem. So you can't just return true here. You have to return whether d is equal to 0. That means it's okay to have leaves. And this is actually like a poorly worded thing, because it says 2 positive integers d and k, but here we see a non-positive d. So
I think
whoever wrote this wrote it wrong. Maybe it was me. This is a non-negative d and positive k.
Yeah, I think the instructions are not quite right.
We're rewriting the problem as we go.
Some of them are
You
hard
should
to
feel free to do this on the exam. Just rewrite the problems if you don't like them. I'm kidding, Joy. Don't do that. Sorry about that, John.
Okay, I think that's a better description of the problem, because obviously d appears to be something that isn't necessarily positive. So this is saying, if it's the case that we've reached the depth where leaves are allowed and we hit a leaf, then we should return true. Otherwise, we should return false. There's a clue here about what to do with this line, b's, which is that the result says all b's. And all is a built-in function that only returns true if all the elements of b's are true. So this needs to be a list of trues and falses, right? And what gives you trues and falses is recursive calls to complete. So we need to be calling complete on something. And as usual, I think it's natural to do this for every b in t.branches. T.branches is just the object-oriented way of saying branches t. And what recursive call will we make? Well, for this to be dk complete, it has to be that for all the branches, they are d minus 1 k complete. So now we get a list of true and false values where they all need to be true in order to get a true result. But something else needs to be true in order to get a true result, which is that it has to be the case that the number of branches at t is equal to this number k, which is the branching factor that's supposed to happen. So this is like a very strict structural description of what a tree looks like, is that it's got like the same number of branches until you hit the leaves, and all the leaves are at the same depth, and here's how you would check for it. So the question is, why is it the case that you can have a different behavior typing ASCII repr than you can calling repr on ASCII? And in general, this is like not important, but I figured if I'm explaining something in Python, I might as well explain it correctly. And there's this weird case in which this can be true, but only if you use the object system in a way that is not really designed, which is that you put a function as an instance attribute. Then these can be different. So if you have a class bear that has nothing in it, and you make yourself a bear, and then what you do is you build a function that does something, like return go bears. And you set that as an instance attribute of the ASCII instance, not part of the class, but just part of ASCII himself. Then you'll get this weird behavior where
Don't
they
ever
print
do
different
this.
things. But you would never do this. It's just like, it's some weird esoteric fact about Python that, it's fine if you would never use this, but it does show the behavior, which is that what repr does is it looks in the class, it doesn't look in the instance, which is like very strange. Almost everything else in Python would first look in the instance and then the class, but this one doesn't.
By the way, one thing Python could have done to avoid this weirdness is says you can't define functions with double underscores before and after the name. Right? That's what's basically happening here is you're making something look like it's a member function using that default nomenclature, but there's no protection of that.
So sometimes when you make something as flexible as Python, then instructors find weird ways to abuse it, and that's, I guess, what I've done here. But yeah, so anyway, what you're supposed to learn is how repr methods, like how you define repr methods within a class. It happens to be that you can't put them on the instance or they won't work. Good question. So why aren't we seeing the str function instead of the repr function? The default str is to just do whatever repr would do. That's just a fact about Python, is that like if there's no str method, then printing something will call the str, but the default str is just to call repr and figure out what that would do. And so for classes that don't have a separate str and repr method, they do the same thing because str just does whatever repr does. So if you kind of want to get them both, you could define a repr method, and then you've kind of implicitly defined a str method because str just does whatever repr does. So for this reason, if you create something that's got no strs or reprs anywhere, we get rid of all this stuff, and we just print the repr of ASCII, we're going to get the same thing as if we print ASCII, which is that by default, the str and the repr-string are the same. It's only if you make them different that they would be different. So the question is about the order of add and radd special methods and what they do. It's just like a very particular thing. But if you want to build a new kind of number, then you have to deal with many cases. In particular, you have to deal with the case where this new kind of number shows up on the left and where this new kind of number shows up on the right. Because it might be the case that something different happens in whether it's on the left or the right. If Python hadn't made plus so flexible, then maybe the order wouldn't matter at all. But it's so flexible, it could be used with strings, it could be used with lists, where sometimes order does matter. And so for this reason, there's two different special methods, one that gets called when x is on the left, and a separate one that gets called when x is on the right. And they're called add and radd, respectively. Yeah, so, well, maybe we'll just do an example, and that might fix things. So let's assume other is an int. How do you add? I think you'd have to return a new rational that's got your old numerator in there, plus it's got other times d in there and your old denominator. And how would you radd? Well, okay, so this is like the x plus 3 case, where other is 3. And how would you radd? Okay, so now we have a different case. This is the 3 plus x case, where other is 3. So what do we return there? We return a rational where the numerator is n plus other times d, and then the same denominator. And then it will work in either case. I think in order to see what's going on, we at least need a repr method, which would return rational of n and d. Oh, I went off the line. It's okay. And now if I have my thing, x, which is like 1/2, and I write x plus 3, I get,
self. Rookie mistake.
Seriously.
The number of times I do that, John.
Then we get 7/2. And if we write 3 plus x, we get 7/2. But we wrote the same code here and here. So one option, instead of writing this out, would be to just write that radd equals add. We had already written it. Why write it again? And then we don't need this anymore. And we get the same behavior. That was what was going on in that example.